Good afternoon. My name is Javier Talavera. I am an undergraduate student at George Mason University, here to talk about our work on the automatic synthesis of virtual wheelchair training scenarios. There are approximately 2 million new wheelchair users in the US every year. This can be due to illness, injury, or disability. Being able to navigate well with wheelchair is important for many of the users, as it may end up becoming their main method of transportation. Certain maneuvers, such as sharp turns or navigating narrow paths, can be difficult and are an important part of learning how to use a wheelchair. Currently, there are 3 main ways to learn how to use a wheelchair. The first involves the use of a human coach. This generally involves one-on-one in-person guidance from an experienced individual and is known to work well and be an effective form of training. The next method is self-teaching through trial and error. Of the 3, this is the least effective. This is followed by instruction by either video tutorial or instruction manuals. All these approaches have limitations such as the time to complete the training, the location of the training, and the availability of when one can receive the training. With the rise of virtual reality, the use of virtual training simulations have proposed effective ways of practicing certain tasks with an element of realism that is not available in a video tutorial or reading of instructions. For example, as shown listed here, virtual reality has been used in training ranging from surgical procedures, driving, industrial maintenance, or even shooting. While there are some simulations that focus on manual wheelchair use, for example this wheelchair simulator, it lacks realistic mechanics and does not focus on the training aspect of the wheelchair. Our approach attempts to solve some of the problems previously mentioned, such as lack and variability of location. We do this by using automatically generated scenarios which can be navigated with a physics-based wheelchair simulation. The approach uses a cost-based system to generate indoor environments with a specified training path for the user to follow. The main characteristics that we focus on for the path are the length, rotations, and narrowness. The difficulty of the path can be adjusted depending on the user. The costs that are used for generating the training scenarios are the pairwise distance, pairwise rotation, path distance, path rotation, and path narrowness costs. There are 2 pairwise costs specified in the training scenario generation. These costs are focused more on the scene generation. A pairwise cost is a cost of an object relative to the position or orientation to another object. With a distance cost, each object has a specified distance cost used to determine a distance from its pair. This cost allows for a reasonable distance between pairs. For example, it would be unreasonable to place a couch up against a TV, nor would it be appealing to have a couch too far away from a TV. The pairwise distance cost avoids such scenarios by allowing a target pairwise distance to be specified by the user. Given the list of object positions as vector v and the pair indices vector e, the pairwise distance cost is denoted as the equation here, where given any pair ij, vi is the position of object I, and vj is the position of object j, and dij is the pre-specified target distance between these paired objects. For the rotation cost, it's similar. An object can specify a certain rotation with respect to its paired object. The orientation of certain objects is important for creating a realistic layout. Without this cost term, objects may face in random directions rather than towards their pairs. The pairwise rotation cost is calculated as the difference between the relative angles of the paired object and their expected relative angles. Given the list of angle rotations of objects denoted as vector theta, and the pair indices vector e, the pairwise rotation cost is denoted here, where given any pair ij, theta I is the rotation of object I, and theta j is the rotation of object j, and delta ij is the target relative angle between object I and j. With the distance cost, a path begins at the wheelchair and ends at the target. The target position is randomly sampled during the optimization process. The path is optimized as the furniture attempts to place themselves around the room. The path distance cost, which measures the difference between path distances p and the user-specified target distance dpath, is denoted here As shown in the right figure, the total distance of a path can be calculated by summing up the distance between every two adjacent nodes in the path, pi and pi plus 1. With the rotation cost, the customization of the path rotation is vital for adjusting the simulation difficulty for a user. For example, if a user cannot navigate turns well, adjustments can be made to have the path gradually increase rotations until the user feels comfortable with turning. The path rotation cost measures the difference between the rotation number of the path p and the user-specified target rotations denoted here, where the rotation Boolean function gamma I returns 1 when pi plus 1 minus pi is not equal to pi minus 1. Otherwise, the function returns 0. As shown in the right figure, the rotation number increases only when adjacent two nodes have different directions. With the narrowness cost, in order to manage the training difficulty with respect to how narrow a path is, narrower paths require more precise control, which mimic training scenarios within a tight virtual space. The path narrowness cost measures the difference between the average narrowness of path P and the user-specified path narrowness npath, and is denoted here, where Qi is the position of the object in the scene S, which is closest to the path node Pi on the left side. Wi is the closest object to Pi on the right side. For optimization of the room, we used an interactive approach which attempts to minimize the total cost of the training scenario. For the path, the optimization is specified using three main costs, as previously mentioned. These are the distance of the path, the rotation of the path, and the narrowness. During the optimization, starting from the wheelchair, the A-star algorithm, a widely used pathfinding and graph traversing algorithm, is employed to generate a random path in each iteration. Randomly sampled paths are accepted when they are closer to the target path than the previous path, until the best path is found, given the currently synthesized layout of the scene. For the room, each optimization step has three types of moves. First, an object moves to a random position. Second, an object rotates to a random orientation. And third, the path target moves to a random position. In our optimization approach, the Metropolis Hastings algorithm is used to find the optimal solution. During each iteration, whether or not to accept a new move is decided by an acceptance probability. This acceptance probability is determined by the total cost of the current status and the proposed status. The total costs use all the costs specified, bounding the range of the total cost function g interval 0 to 1. The acceptance probability function is dependent on the number of iterations. At the start of the optimization, the temperature is set to 1, giving the optimizer a higher probability of accepting incorrect moves. As the iterations increase and the temperature decreases, the algorithm becomes more greedy and less likely to accept worse moves than before. When the optimizer reaches its final stage, all bad moves are discouraged and minimized to a probability close to 0. As you can see in the image below, objects are randomly initialized in the room, and as it goes through each iteration, it begins to find the optimal solution. Weights are placed on certain costs to prioritize different moves. Moving on to the navigation within the room, the wheelchair simulation is done using HTC Vive trackers attached to the wheels of a manual wheelchair. This allows for precise tracking of the wheel's location. The wheelchair with the trackers attached is raised up to keep the wheels off the ground. Moving the wheels of the wheelchair moves the virtual wheelchair. We can calculate the angular speed of both sides of the wheelchair, w of t, as a function with respect to time t, as shown here at the top, where rt is the radius vector of a wheel, which is defined, which is the second function, and delta t is the rotation direction of wheel defined at the bottom. In our simulation approach, the wheelchair is always facing along the z-axis. Wheelchair movement in the simulation is done by translating and rotating the scene rather than the virtual wheelchair. For example, when the wheelchair seems to move forward in the simulation, it actually remains static while the scene moves past it. In order to test the efficacy of our training environment, users would be asked to go through a physical course using a manual wheelchair. They were given a predetermined path made up of bottles to follow, and the bottles knocked down and time it took to complete the course were recorded. The procedure was performed both before the training simulation and after for a post-evaluation. If you look at the chart below, each circle on the chart corresponds with a bottle in the path. The number associated with the color is the number of times that bottle was knocked over. The virtual training consisted of 9 scenarios with varying levels of difficulty, some with more path rotations, longer distances, and narrower paths. This allowed for users to practice different maneuvers. Here were the 9 scenarios that each user went through. There were 3 with long paths, 3 with high rotations, and 3 with high narrowness. Results. This figure shows the bar plot. The figure on the left shows the bar plot of pre-evaluation in blue and post-evaluation in orange. There were 15 users in total. The figure on the left is the number of bottle collisions, and the figure on the right is the time to finish the task for each user. In order to measure whether the improvement of the user's skills in controlling a wheelchair is significantly improved, we applied the ANOVA test to compare the pre-evaluation data and post-evaluation data. In our case, the factors are time duration and bottle number. Therefore, we have applied 2 separate one-way ANOVA tests. The time duration factor measures how efficiently the user can control the wheelchair. The null hypothesis assumes that there is no significant difference between the mean value of the time to finish the pre-evaluation and the mean value of the time to finish the post-evaluation. However, we can prove that there is a statistically significant difference between the two. As calculated, the p-value was equal to 0.0036, which is less than 0.05, meaning there is a statistically significant difference in the time duration to complete the task before VR training and after the VR training. The mean finishing time for the pre-evaluation was 89.9 seconds, and the mean finishing time for the post-evaluation was 67.13 seconds. Therefore, we are able to reject the null hypothesis. The null hypothesis for the bottle collision suggests that there is no significant difference between the mean value of the number of bottle collisions during the pre-evaluation and the mean value of the number of bottle collisions during the post-evaluation. The mean number of bottle collisions for the pre-evaluation was 4.13, and the mean number of bottle collisions for the post-evaluation was 1.6. The calculated p-value, 0.0035, which is less than 0.05, means there was a statistically significant difference in the number of bottles knocked over. We can conclude that both the proficiency and the precision of the wheelchair control reject the null hypotheses and strongly validate our VR training. After the users completed the training, they were given a survey to complete to see what they thought of the training. Most users had a positive experience with the training simulation and found that it was indeed effective, enjoyable, comfortable, and so on. For future works, adding a control group and introducing penalty reward mechanisms to increase level of entertainment are things we may look into. Also, expanding the size of the environment to a whole house instead of a simple room and attempting to simulate outdoor environments are also things to look into. Thank you for listening.